So I'd like to present some musings that I mused on the plane from Nanjing a couple of days ago. I've heard it said that the sincerest form of flattery is plagiarism. And I will demonstrate that point through this talk by showing a number of slides that Martin very kindly left in Nanjing from his short course. Silly thing to do. Anyway, so I'll be musing on the subject of the Ediacaran-Cambrian boundary, phosphorus and oxygen. Phosphorus is a very, very interesting element and links very tightly with oxygen. In a way, it acts a bit like a source and a sink for oxygen. So phosphorus, the only source of phosphorus is weathering. Nutrients go into the ocean. That helps to bury carbon and release oxygen, as you well know. But there's another side of the coin. Under oxic conditions, phosphorus is more efficiently buried, and so it can actually act as a sink for oxygen, and so stop further oxygenation, like a negative feedback. All sorts of interesting positive and negative feedbacks about phosphorus and oxygen, and that's what I'm going to muse on today. And what better place to start than Weng'an? This is Weng'an in Guizhou province, which is the site. It's a quarry, a phosphorite quarry. It's the site of the famous phosphatized embryos of whatever animals or whatever takes your fancy. So let's start there. Let's retreat a little bit. What is the Ediacaran-Cambrian boundary or the Precambrian-Cambrian boundary? And Martin has phrased this as Darwin's dilemma in his book. And we all know about this. Darwin was thinking, well, if my theory is correct, then where is the evidence for all of these early stem group organisms? We suddenly get trilobites at the base of the Cambrian. So what's happened? And many people have had different hypotheses about that. And Martin put them into categories, and he gave them names. So we'll have a look at some of those in a moment. The first category, of course, is that, there we are, was what Martin named Lyell's hunch, which is that it isn't like an explosion, that there's a hidden record there somewhere. And there's sort of a taphonomic artifact. But actually, we now know the Cambrian explosion was indeed a real event, and part of the work that went towards that owes a lot to Martin. So Martin was one of the pioneers in what I would call integrated stratigraphy. When I started my PhD at the ETH in Zurich, I looked at strontium isotopes and carbon isotopes and tried to combine them with the biostratigraphic record of trace fossils, small shelly fossils, and the emerging stratigraphic framework from geochronology. So this is how I summarized that in 1999. It's not so far different from today, going from cryogenian, we call this now the Ediacaran, into the Cambrian, and trying to tie all those different things together. And using that evidence, you can see that the Cambrian explosion was indeed a real event. And now that fossil record is getting better and better and better. We now there's a real diversification event. You can see that with trace fossils. Things get bigger, things get more complicated, and start to do interesting things like make shells and penetrate into the sediment. We've heard a lot about bioturbation already today. And that's for the first time in Earth history. Gone are all those pseudo-Precambrian trace fossils from way back when. Now we know that there's something really happening in the latest Ediacaran, which is new. So let's get rid of what was called Lyell's hunch. Now, there's also intrinsic explanations for this explosion. So things like Hox genes, where it takes a long time for these to develop. And that just happened to take place during the Ediacaran. And there are extrinsic, so-called permissive environment explanations, and there's all sorts of ones like that. And the most common, of course, the favourite one is oxygen. That oxygen reached a certain threshold beyond which animals could diversify, get big, have muscles, and start to mobilize the sediment and things like that. So in the last few years, co-evolutionary hypotheses have been all the rage, and I'm going to talk a little bit about that. That's sort of combining the extrinsic and the intrinsic. So if you like, there are extrinsic drivers like tectonics, like the solar evolution, and you have intrinsic co-evolutionary feedbacks on top of that. That extrinsic factors can allow something to evolve, and that evolution itself feedbacks into the environment. and it's quite complicated. So you need to do modelling for that. So right at the end of this, I'm going to look at some modelling experiments that Martin also was involved in and I was involved in. Let's have a look at some of these other extrinsic factors. I like them quite a lot. They go back way back when to Abraham Gottlob Werner, who believed that temperature was the key. Some people still think that the earlier Precambrian was very hot and then it just got cooler. And when you got cool enough for animal-grade organisms, they just started to evolve. I don't believe that. Ocean composition. My favourite one here is this one. I don't hear much about this anymore. Mitter in 1989. When people started to use artificial seawater to grow fish in their tanks, they realised that the fish didn't swim very well. In fact, they didn't. They just sort of hopped along the bottom of the tank. And the reason for that is that people thought you could just mimic seawater by putting the right amount of sodium, chloride, sulfate, magnesium together and forget about the trace elements. And it seems like strontium is key to biomineralization. Who would have thought it? And so the idea was that there was a threshold not for oxygen but for strontium, and then strontium got beyond a certain threshold, then biomineralization was possible. Probably a little bit naive. And there are other examples, a bit more co-evolutionary here, saying that snowball Earth had something to do with that. Sorry, widespread glaciation. And then oxygen. Oxygen is the key. So I'm going to focus really mostly on oxygen today. So this goes back to Nursel, 1959. Oxygen overcame a crucial threshold, and that idea has been around quite a long time. There was a lot of organic burial towards the end of the Precambrian, possibly tectonic in origin. That released lots of oxygen in the atmosphere. So essentially nutrient-driven. That's where the phosphorus comes in. Unfortunately, it's a little bit more complicated than that, and we tried to summarize this. I would draw this completely differently these days. It's only a few years ago. And Rachel's already shown this a little bit. So some of the earliest evidence is from carbon isotopes and strontium isotopes, just to show that there's a lot of burial of organic matter which would release oxygen. Carbon's a little bit more complicated than that, so we really need to model that. Nobody's gone back to this until now, and I think it really needs to be done. One thing I would note is actually carbon isotopes, at least their average, tend to actually go down towards the Precambrian-Cambrian boundary. They do the opposite to what you'd expect. So either there was a much earlier oxygenation as a result of organic burial, or we just don't understand the carbon isotope cycle, and I think the latter. Focus recently has been on these proxies, sulfur isotopes, trace elements, and more recently on the chromium. But one thing is worth talking about here is that here we're not just talking about the atmosphere. We're always assuming, oh, there's atmospheric oxygenation. But these proxies actually relate to the marine environment, and there's a big difference between the atmosphere and what happens in the marine environment. And many of the proxies, like sulfur isotopes, actually relate to what's happening in the sediment. So complex redox cycling within the sediment. That may be related to bioturbation and not directly related to any atmospheric or even ocean oxygenation. So we have to bear that in mind, and we need proxies which are global in extent and relate to the atmosphere or to the ocean, or at least to something that we can quantify. Anyway, let's have a look at some of these trace elements. You've got vanadium, molybdenum. There's a huge rise in the concentration of some oxyanions, like vanadium or molybdenum, in black shales across the Precambrian-Cambrian boundary, and that's telling us that there is a reduction in the sulfidic sinks across that boundary, and I'll show you more evidence for that in a moment. So that's indirectly related to oxygenation. So there's some arguments that the ocean, the deeper ocean, becomes ventilated, becomes oxygenated around this time, and this is a well-known plot from Newfoundland using ion speciation. I won't go into the numbers, but basically they show us that as you get into the fossil-bearing strata in Newfoundland from the Gasquez glaciation, you start to get ion speciation signatures which show oxic conditions. You're clearly going from anoxic bottom waters, seafloor, to more oxic conditions, at least in this one part of the world. It is a local proxy, possibly a regional proxy, and may not have global significance. But it does tell us that the organisms that were sitting on the seafloor there were enjoying oxic conditions. But does that give us causation? Probably not. So we're left with a dilemma. Were these fronds, these fractal organisms, these supposedly animal-grade things, were they exploiting the oxidized environment, oxidized perhaps by some extrinsic factor, or were they engineering it? So the evolution of things like simple stem-grade sponges or other things that we can only dream about, maybe they were filtering out organic matter from the sea and actually ventilating their own environment bit by bit. Or was it a bit of both? It's chicken and egg, and as in the case of chicken and egg, it's probably a bit of both. So that's where coevolution comes in. A key thing in this story is that as soon as we start to get these deep marine oxic environments, and this is Alex Liu, one of Martin's PhD students, we start to find evidence of mobility. And as we get much closer to the Precambrian-Cambrian boundary, that mobility turns into churning of the sediment. To test what happens first, so in what order, and to what extent, we need different proxies. And so this is stuff which is now in Science in Review. So it's new. It's always nice to show something new in a talk. And I'll just walk you through this very slowly. Well, that depends how much time I've got. But anyway, does this shine a thing? Okay. So 5 minutes towards my 5 minutes, or yes, okay. Thank you. I'm glad you clarified that. Molybdenum isotopes. This is delta 98, 95, 96 in this case, 95. It's a compilation of all data plus lots of new data from China. So this is the whole geological record in here, and we see something also happens at this point. The concentrations go much higher. I've shown you that already. But also the isotopic ratios go much higher, and this is the modern value of 2.34. It's normalized to international standards. And you see the first time that happens is around here, Precambrian-Cambrian boundary. So we need more data, but that's saying the same thing as we're getting from here. Okay. Higher molybdenum isotope ratio. What does that mean? Molybdenum isotope ratios is telling you about the global extent of sinks, euxinic versus suboxic and oxic sinks of molybdenum. And it's telling you that at that point in Earth history, somewhere there, we get the first modern-like distribution of euxinia, anoxia, and oxic conditions. If you look in more detail, up here, this is the same data, but actually expanded a little bit. You can see a nice rise from the latest Ediacaran, so the Miao-He biota, into the, so this is the best one to be looking at here, stepwise rise to 2.34, the modern value, by about 520 million years. And that's very interesting. That's the age of the Chengjiang fauna. That's the age of the first penetrative biotubation. And very handily, Gabriel Mangano recently showed a global compilation of biotubation index, which, although we all know this anecdotally, it's nice to see it shown in a quantitative fashion. We can use the biotubation index to sort of to correlate with that change in molybdenum isotope ratio. So with data like that, it's quite complicated. So you need to model it in terms of sources and sinks. So that's what Chen Shi has done at Nanjing University, together with myself and Simon Poulton. And you can see that to go from a Precambrian kind of value here into a modern kind of value, there's not many places where you can go on this space. So this space here is actually unrealistic. You can't go into this space. So this blue line is the modern ocean delta, in this case 98, 95 molybdenum. You can only really go into this space here to actually get to 2.34. That's telling you that for the first time in Earth history, you have a very small global euxinic sink of molybdenum. It's retreating to the margins, places like the Black Sea, places like China. China at this time is quite stinky, euxinic, sulfidic, but it's one of the only places in the world that is. And you're also very high on this chart, which is telling you you have a very large oxic sink. So no matter what you're doing in your one section with your ion speciation or whatever you're looking at, the molybdenum isotopes is telling you a global story, that you're ventilating the ocean on a global scale. This is what we really want to look at, because often we look at empiric basins, very marginal. We're not quite sure what relevance that has to the world as a whole. So I'm quite excited by that. So we've been working a lot on this time interval. So this is a recent compilation. And I just wanted, this is the carbon isotopes here again, very, very wild. And these wild swings disappear, really, as we get to the middle and upper Cambrian, which is very interesting in itself. More or less coincident with the increase in bioturbation when you get into Cambrian stage 3. So coincident with these high molybdenum isotope values. Now, bioturbation is very interesting because it changes the whole world. And one of the first people to really look at this, and it's very nicely shown here, pictorially by Martin, another slide I stole from a short course. We can see they're going from a Precambrian world of a very narrow redox boundary. We go to a very extended redox boundary, an extremely complicated situation, lots of redox coupling reactions on the margins of burrows. pH also goes from a very sharp change, basically at the microbial mat stage, to, again, a much more extended change, but also to lower pH because you're introducing oxygen into the environment. You're making the pore waters more acidic. Both of those things actually change the cycling of phosphorus. Phosphorus will be trapped at this point. It will be trapped by the changes in pH, which I won't go into right now. It will also be changed by the oxic conditions. If you have an oxygenated seafloor, you will trap more phosphorus than if you have an anoxic seafloor. This has been done experimentally and has been shown also with rocks and sediments. So this change here will not only have changed the availability of oxygen, it will also have changed the sink, the phosphorus sink that I was talking about early on. And this is modelled by Richard Boyle, who's a very clever guy down in Exeter who's just moved to Denmark. And lots of these different figures you can see in his paper, in our paper, which is now published in Nature Geoscience. This is the postulated oxygenation, which is possibly an extrinsic thing, we don't know, through the Precambrian-Cambrian boundary. It doesn't really matter even if that was flat. We could have it flat, it doesn't matter. But as soon as you get into bioturbation, penetrative bioturbation, you actually reduce the world's inventory of oxygen and of nutrients. It's basically a negative feedback. As soon as the nutrient and oxygenation goes into overdrive, the bioturbation and the oxygenation pulls that phosphorus back down and stops the world going overboard. It's a classic negative feedback. And I gave a talk here last year looking at this, the centrifugal governor, which was a prime motivator of people like Alfred Russel Wallace and Charles Darwin. It's a dynamic self-regulatory system. And bioturbation helped to tighten those negative feedbacks. If you want to test that, did oxygen actually decrease? You can again look at the molybdenum isotope ratio of seawater, and there is a suspicion that there is a decrease in the global extent of oxic seawater. You're a hard man. You're a hard man.
You seen those sticks behind you there?
So it's all about negative feedbacks. I can sense negativity. The key point then I wanted to make today, I'm musing, so I can say anything I want really, is and being inspired partly by Martin Brasier and his very eclectic was the word I was looking for, eclectic and integrated view of the world, and this is what we call nowadays coevolution with its negative feedbacks and positive feedbacks, and we can use modelling and isotopes to quantify that. So this is what we just published in Nature Geoscience, Tim Lenton and myself and others, Nick Butterfield also in the room, as we can look at how, if we ignore the extrinsic factors, how the intrinsic factors can actually change, start to ventilate the ocean as you go through from the Cryogenian to the Ediacaran into the Cambrian. And as you start to have these new behaviors, you can store phosphorus and introduce new negative feedbacks into the world. So thank you very much.